work at Harbor Branch Oceanographic Institute. I've been there for a little over a year. As David said, I used to work at Wet Labs. I worked there for 15 years. And I've been introduced, not only here, but many other places, as the guy who used to work for Wet Labs. So it's almost like the artist formerly known as Prince, you know, it's sort of my identity. But it was 15 good years at Wet Labs. I started in 2000 after my postdoc. I opened up a research branch in Rhode Island. For those of you who know Wet Labs, they're based in Oregon. So it was across the country, and it was, in the beginning, it took, nerves of steel to get it going because it was all soft money funded, so funded by external contracts. And I just rented an office, and I had a lab, and I built up the lab myself, and then over the years we were able to grow it. And then move into our own dedicated facility, and then last year I left. It was just a good time to leave for a variety of reasons. But it was very many good years at Wet Labs. I would say 12 good years at Wet Labs. And one of the great aspects of working at Wet Labs is to work with a great team of engineers who we could collaborate in developing new technologies. And the technologies could be used to address scattering and other ocean optics problems. And something I really enjoy, developing new technologies and then applying it to tough problems in our field. And now I can still do that at Harbor Branch. There's a great ocean engineering group there led by Fraser Dalgleish, and we're already starting to collaborate on some new sensor development efforts. So earlier this week, you guys got a lot of fantastic knowledge from Kurt, Darius, and Zhongping on IOPs and specifically scattering. I'm just going to very briefly go over some of the basics just to kind of reinforce that background. Darius specifically talked a lot about interactions of particles with light, and a lot of that is relevant to what I'm going to talk about today. And I had many slides in there that overlapped with what Darius said, and just when I thought there was something he wasn't going to say, he said it, which is great because he can say it much better than I can. And that means I can focus more on the experimental aspects here. And then Zhongping also introduced, the IOPs and their subfractions. So I'm not going to go into detail on that. I'm just going to have a couple slides here that just reinforce that. So radiative transfer, you guys have learned about from Kurt, where you have this radiant beam of light traverse a medium. There's some loss due to scattering, losses due to absorption, and there's sometimes gain from scattering from other light that's scattered into that exact orientation, that theta and that azimuth. And absorption plus scattering equals total attenuation. So if you learn nothing from the lecture, hopefully you'll take that home with you. Inherent optical properties include scattering. These are the properties that depend only on the substances in the water. The apparent optical properties depend on the IOPs as well as the light field itself. So today I'm going to focus on scattering. And all of the different scattering parameters that we're going to talk about can all be derived from the volume scattering function, which describes scattering as a function of angle. So it's defined as this radiant flux or intensity as a function of angle normalized to the incident irradiance and the elemental volume that is derived from where the intersection of the source beam and the detector beams are. You can think about the measurement of volume scattering function, which I'll talk a lot about in detail later, but it's always some range of angles that ultimately are resolved because of that dV can never be small enough. You need a big enough dV to get a signal, and for a variety of reasons in the ocean, you need a big enough dV so that you're looking at enough particles so you don't look at individual particles. You get a lot of spiking and very, very noisy data. So again, all the scattering properties that we'll talk about today can be derived from this. And then for radiative transfer, the only two functions as far as IOPs that you need are the absorption coefficient and the volume scattering function. So this is a polar plot. You guys have seen some polar plots this week. This is a polar plot of a volume scattering function, a very famous volume scattering function from Petzold in 1972. And this was the standard for many decades. Before, I'd say, the last 5 to 10 years, there have been several other volume scattering function devices that have been developed and are starting to be used by the field. But this is a polar plot, and each ring here is an order of magnitude in intensity. And the incident rays coming from the bottom of the slide, your dV is right in the middle here, and then this is the distribution of scattering. And as you can see, this is 0 degrees here. So this is 0 degree scattering, this is 180 degree scattering, 90 degree scattering. You can see it's azimuthally symmetric. That's just the way it's plotted. It was measured as a semicircle of detectors, or really a single detector that was rotated through a semicircle. But the main point here is there's a huge dynamic range in intensity. So it's very, very steeply forwardly peaked. And you have a total range here of 7 orders of magnitude. So from a measurement point of view, it makes it very challenging to resolve intensity over such a large range. And then here are some volume scattering functions that were measured in Scripps Pier. And just to show you some of the difference in shapes that you get in different locations. This is just a single time series, and I've plotted a bunch of the VSFs on top of each other. But I've highlighted the background here, which has, these are all normalized. So the background here is lower backscattering than the other VSFs I'm showing. Sediment-laden backscattering is a higher backscattering value, relatively hard particles, high refractive index. And then bubbles are an interesting case that has this mid-angle enhancement here, which I'll talk about more later on. Yeah, and so typically, obviously, if you integrate just this back hemisphere here of scattering, it's only about 0.3 to 3% of total scattering. It's a very small amount, and obviously that's very important for applications like ocean color remote sensing. So to integrate, to get total scattering or different ranges of scattering, Kurt showed this here, this unit sphere, where you have, again, the light beam coming from the bottom of the slide. It hits your dV, and then it's imaged onto this unit sphere. And what we need to resolve to integrate is this annular ring here of scattering. So the perimeter is 2 pi r, and then r is defined as the sine of your scattering angle. So the solid angle then is 2 pi sine theta d theta, which goes into the integral. So you have 2 pi sine theta beta theta d theta. And so this 2 pi sine theta effectively weights the contribution of beta to b. And importantly, at 0 degrees and 180 degrees, beta pi, beta is non-zero, but its contribution to b, when you go to the limit at exactly 180 degrees, is 0 because of that sine theta weighting. If you guys have any questions at any time, feel free to interrupt. So Zhangping talked about the partitioning of scattering into components. So total scattering can be partitioned into scattering due to water and scattering due to particles. The particulate fraction can be further partitioned if you'd like, and most of the time it's done in a very conceptual way where I'm going to partition it in terms of minerals, different phytoplankton assemblages, dinoflagellates, diatoms, cyanobacteria, whatever. And you can keep partitioning it all the way down to the single cell, so they're all additive. And as Darius mentioned, there's something called the law of independence, where as long as those different particles are separated by at least 2 times the radius, you can add them independently. If they're too close, you start to get diffraction patterns that interact between the particles, and so you get what's called coherent scattering. You can also partition with respect to angle, where you do this integration and then you choose your wavelength range that you want to integrate over. So for total scattering, ideally you'd integrate from 0 to pi here. So 0 to 180 degrees. Forward scattering at 0 to 90 degrees, and back scattering is 90 degrees to 180 degrees. And then other scattering properties, you've heard of the phase function, where the volume scattering function is normalized to the integrated total scattering, and the asymmetry parameter for the volume scattering function, where if you've got a symmetric volume scattering function around 90 degrees, or if it's isotropic, the g is 0, and if it's highly askew, g starts to tend towards 1. So here's an example of some volume scattering function data that was collected in Santa Barbara Channel a few years ago. And one of the practicalities of measuring the volume scattering function is in the near forward direction. This isn't a log-log plot here. And I know this is very difficult to see, but this is 1 degree, and this is 100 degrees, so 10 to the 2. But measuring volume scattering function in the forward direction requires a different method than it does at larger angles. At larger angles, you can have kind of the image I showed before where you have a light source and then you have a detector that can look at different angles. But once you get towards the near forward or the near backward, you need another technique, and so there's something called diffractometry that's used. And the LIST 100X is a diffractometer on the market right now that I'll talk a little bit about later on. So the LIST is measuring here the volume scattering function in the forward angles, and the mascot that we have, it's a prototype volume scattering function device in our lab, measures the larger angles out to 170 degrees. And if you've calibrated everything very well, 2 totally independent methods, they should agree very well where they overlap, which in this case is at 10 degrees. And for the most part, throughout these data sets, that's the case. You can see each one of these is an individual profile, and I've taken each of the VSFs from the profile and superimposed them on each other. And you can see some interesting shapes. So this is at the surface here, and then down deep you get a straighter VSF. But this is an indication, as Darius was alluding to the other day, of different particle types. So different particle types scatter in different ways. Specifically in the near forward, when you get a flatter shape to the volume scattering function in the forward direction, it's indicative of more small particles. And when it's more steep, you're looking at larger particles. And the LIST is actually sold primarily as a particle sizing device, not as a volume scattering function device. That's how the vast majority of people use it. I think probably myself, Emmanuel, maybe Darius, Derek Gray. There's a handful of people in the world who really use it as a volume scattering function meter. But what it does is it's got this black box software that takes the volume scattering function information and inverts it to get particle size, and it's based on these shapes here. And the way it does it, actually, I'll briefly mention, is it's got 32 different sizes that it calculates the volume scattering function. Each one has a different shape. And then you take the measurement, and it fits those volume scattering functions to the measurement to then derive the relative contribution of each one of those fractions.
Can you repeat how does it mean to make the difference between the different components?
Sure. So it has 32. This VSF is measured at 32 individual thetas, and they're logarithmically spaced. And so you've got 32 degrees of freedom to use in an inversion. So then they have 32 different volume scattering functions that are modeled for different particle sizes. And the primary way it was done originally is with modeling assuming spheres, perfect spheres, homogeneous spheres. So they use what's called Lorentz-Mean theory, which Darius talked about a little bit. And then once you have that library of functions, you have your measurement, and you fit the whole library to the measurement. It's essentially eigenvectors, and then you can come up with an amplitude for each eigenvector and add them together. That's how you get, and then you add them all up and you get your full size distribution. Here's some other volume scattering functions from all over the world that we've collected over the last 10 years or so. What you can start to see here in the last few years, so in these beginning years, I had a guy working with me, Matt Slivkov, very, very good technically. He's working with David now. And one of the things that he took on in the lab was to maintain the VSF, calibrate it, and do everything you need to do to get the best quality data, which is a real challenge. In the last few years, there's been some issues with the calibration, which is what this is showing here. And this is at the larger angles. So if we get rid of this, there's actually a pretty good lineup still. But the best data we have goes back to these first years where we had the list in our lab and Matt was working with us. And if you look at here, this starts to blow up a little bit, but that's just a signal to noise issue because it's very, very clear water. So one of the things you can do to test closure between instruments, so what I was showing you before with marrying up the list data and the mascot data was closure in a way because they're both measuring scattering at 10 degrees using different techniques, and they agreed pretty well. you can integrate the volume scattering function. In this case, we can integrate between 0.9 and 180 because we're comparing it to the total scattering derived from an AC9. So the reason we're integrating from 0.93 to 180 is because the AC9 C channel has an acceptance angle issue that I think Emmanuel mentioned the other day in the practical. So transversometers that measure C never measure true C, because to measure true C, you have to have an acceptance angle for the collimated detector optics that goes to 0. And if it's at exactly 0, you have no light. So you have to open it up a little bit. There's a compromise there. With the AC9, they've opened it up to 0.93, so you're collecting all the light between 0 and 0.93. So to compare to the VSF, we've integrated from 0.93 to 180. And this B was derived from taking that C, which is A plus B, well, A plus beta integrated between 0.93 and 180. Then we subtracted the A from the other channel, the reflective tube absorption meter. That's how the B was derived. So you can see it's a pretty good correlation. It starts to deviate a little bit at higher values, which I think is because of the correction that we use for scattering for the reflective tube absorption meter for this particular data set, which you guys haven't done yet, but you're going to learn about. I have one slide on it today, but you're going to learn about it in more detail, I think, from Emmanuel and Colin. You can also do things like look at the cumulative scattering contribution. And so this is integrating between our smallest angle, in this case it's 0.079 on the list, to whatever other angle we're looking at. So if we're looking at 1 degree, this value here was obtained by integrating from 0.079 to 1 degree and then dividing by the total VSF just to get the contribution from 0 to that particular angle. And what this is showing is that your cumulative scattering very, very rapidly ramps up. So even at 3 to 4 degrees, you already have about half of your scattering completely accounted for. It's a very, very steep volume scattering function. And then I mentioned the average cosine. It kind of looks at the skewness or the steepness of the function. And this shows a nice relationship between the backscattering ratio and that average cosine. And that kind of makes sense because if your relative backscattering is increasing, it's getting a little flatter. And so the amount that it's skewed will decrease, and that's what this shows. And 2% here is a relatively high backscattering ratio, and it goes down to about 1% here, so that's the range we're looking at. This relationship was also noted in this paper by Lee et al. And it had the same slope, but it's offset, and it's offset because they're integrating over a different, they have a different minimum angle. They have 0.6, and we're starting at 0.079. And then we also looked at the relationship with turbidity and didn't find any, which is just saying turbidity wasn't related to particle composition. So in talking about the shape of the volume scattering function further, Zhongping talked about different modeling, analytical modeling algorithms that are out there. Beardsley-Zonafeld 1969 is one, and this is the equation. As you can see, it does very, very nice in the backward direction, but does not do so well in the forward direction, exactly how Zhongping stated it. And this is also noted by several others, but it's a very useful function to map out the backward direction. So Hennier-Greenstein was also mentioned, and as Kurt mentioned, it's not the best way to parameterize the volume scattering function. And there have been a lot of people who have tried to alter it over the years to make it fit better. Katawar first took the Hennier-Greenstein function and made it into a two-term function, so you have more variables to fit. And then Vlad Haltrin later on took that two-term function and turned it into a one-parameter function. So that's what I'm testing here, and you can still see it really doesn't do that well. It doesn't fit very well in the forward direction. You overestimate in the mid-angles, and you underestimate in the backward direction. And again, this is a log-log plot, so this is a huge underestimation. This is a big overestimation, et cetera. So Kopelevich, I think that's how you pronounce it. Is it Kopelevich or Kopelevich? Kopelevich?
He's my boss.
Oh, he is? this is an awesome regression. It actually is a very, very good algorithm. So what he did was empirically said if we combine two different phase functions, kind of two different basis vectors, and just fit them to the volume scattering function, we should have a good fit. And what that's saying is that the volume scattering function shape isn't going to change too much. So you can just take a kind of, he has this small particle high refractive index phase function and then a large particle low refractive index phase function. Then you can mix and match them in different ways to reproduce whatever VSF that you measure. Or in his case, he's got an algorithm where if you have the number of particles, you can actually estimate your phase function shape. I'm not really using it that way. I'm just seeing how well this could possibly match the data sets that we've collected. And you can see greater than about 0.6 degrees here, it has a very nice fit. Doesn't really do so well in the near forward. But what's happening is really in every one of these cases, all the fits that I've done, this small high N, if you want to call it that, completely dominates in the backward direction, and then this large one dominates in the forward angles. But overall, it's a pretty good fit. And this is another data set. It was collected 2 years ago for the Sabre cruise in the Northwest Atlantic. Just showing, unfortunately, the fits here are covering all of the actual phase functions, but they're excellent fits, so it's a good approximation. And the total root mean square error is about 9%, so it does a really good job. This is just looking at 10 to 170, so this is just the mascot data. Then we come to the Fournier-Ferrand phase function, and Zhongping showed all the equations in his slide. I don't have them here, but what George Fournier did and his colleague Ferrand is they modeled the different components of the phase function. So there's a model diffraction. So there's a very good model for diffraction. They came up with an approximation for that. And then they looked at the models for refraction and reflection, and they came up with a good approximation of that. And took all these approximations and put them all together. And what's really beautiful about it is it's all rooted in physics of scattering. So it's not, everything else is empirical. It's all rooted in the physics. Not only is it beautiful in the fact that it's rooted in the physics, the fits to the actual data for the full entire range that we can resolve with our instrumentation is exceptional. It's almost always exceptional. The two inputs for their algorithm are the bulk refractive index of the population and the slope of your particle size distribution. So not only is it rooted in physics, has an exceptional fit, but if you can code it pretty easily, and it's pretty easy to then fit it to volume scattering functions that you make, that you measure. And then once you do that, what you get out the other end, it's kind of an inversion. You actually solve for your refractive index and your slope of the population. So you're actually getting really meaningful information about the composition of the particles with this algorithm. So it's really a brilliant algorithm. It's a huge, if you ever want to use phase functions, I know Hydrolite uses Fournier-Ferrand phase functions, but this is the model I would recommend. It's great service to our field ever since he came out with it. I would mention, though, there are some cases that I've found where the volume scattering function that we measure just doesn't quite have the bow that you need to match up with some of the measurements that we've made. And this is in the mid-angles from about 1 to 70 degrees. And if you look, this is looking at the power law slope. So as you can see, the power on a log-log plot should be about a line. You can see that it gets steeper and steeper and steeper as you go to larger angles, and that's what this is showing. It gets steeper and steeper. And it just doesn't quite get steep enough. So what we started to do now is go back to more of a statistical analysis. This is a cluster analysis after Tim Moore's work. And so Tim Moore derived these based on data sets that I've given him. And so he originally used this technique for remote sensing reflectance. So if you're familiar with his papers, he's got classification schemes for different remote sensing reflectance measurements. I think there's 8 different classifications that he uses. So we're trying to adapt that to volume scattering functions. And so what I've been trying, at least initially, is 2 clusters. Since 2 clusters work so well for Kopolevich, I want to try 2 clusters. And the 2 clusters that we came up with actually are very, very similar. And again, this is a log plot. But, and this is quite a big difference, but it's quite similar. This is a dramatically more dramatically far, the end members are dramatically farther apart for the Kovalevich. And the cluster analysis does a great job of fitting even these hard to fit volume scattering functions. We're taking the root mean square error from 17% to about 7%. And if you then fit it to a variety of other data sets, the fits are typically really good with root mean square errors between 5 and 10%. Sometimes like Hawaii, it's a little higher, but this is driven in part by just the signal to noise of the measurements that we're making in very clear water. So this root mean square error is looking at not only the bias of the fit, but also just inherent noise in the measurements that we're making. And then for the data set that it was initially designed for, it has obviously an excellent root mean square error. So this was designed just for this data set. He's recently done a 2-cluster analysis on all the data that we have. So that's the next thing that we need to do is apply that. So one thing, I'm not sure if Darius talked about this in the second lecture the other day, but is coherent scattering at beta 180. And I'm just mentioning this because it's something that as a community I think we need to think about. As Darius mentioned, if you have these particles separated by at least twice their diameter, then you have independence. You have what's called incoherent scattering, so they can all be added independently. The only time where that seems to fall apart, where the law of independence is essentially satisfied, is at beta 180. And you start to get phase interactions in the scattering between the different particles, and it gives this enhancement over what you'd get with typical incoherent scattering. And you can see that if you've ever flown in a plane and looked at the shadow of the plane, sometimes you can see a ring. You see this all the time when I fly. And that's exactly what it is. In atmospheric optics, they call this the glory. But it's something that's very poorly studied in our field. There used to be a beta 180 sensor that was made by Sequoia, the LIST beta 180, I think, and I don't think it's commercialized. So there's very, very few measurements on this, and there's a lot of techniques like LiDAR, where it's sending out a LiDAR pulse, and it's looking at the return signal as essentially beta 180, and we need to characterize this effect a little better if we want to interpret those signals well. So now I'm going to move to polarized scattering. This is really, really quite simple. Okay, you've got a Stokes vector. I think Kurt described the Stokes vector. You have 4 different elements that describe the total intensity, the vertically and horizontally polarized light, the obliquely polarized, minus 45 and plus 45, and then this is circular polarization. So this is your incident beam here, and this is your scattered beam, and then this matrix here called the Mueller matrix describes how it's the transformation of the incident beam to the scattered light field. And it's for a scattering event. Scattering event could be a single reflection off a surface. It could be the reflection or the total scattering of a cell, or it could be the scattering event could be the scattering by a bulk population, as long as that law of independence is satisfied. And the way this matrix works is this first row is looking at the transformation of these 4 elements of the Stokes vector into unpolarized radiation that's scattered in the scattered beam. This row is looking at these 4 into Q, and et cetera, into U, and then in V. Okay, your circular polarized radiation. This one right here, which is looking at unpolarized incident intensity to unpolarized scattered intensity, is your VSF, or the phase function. We've looked at this parameter a lot with our measurements. I'll talk about it in a minute, but there's also a lot of information in the vertical horizontal polarization. Nominally, the S13 and S14 are 0 at all angles. And I'll show some examples. But if they're non-zero, then this can be an evidence, some evidence of particle orientation. So we're starting to look at that as well. And the other one I'll point out is this S22 can be an indicator of particle non-sphericity. And each one of these elements has wavelength and angular dependencies. So there's potentially a lot of information. There's a lot of redundancy. Essentially, this part of the matrix is all you need, because when particles are randomly oriented, because this part of the matrix is just a mirror image. But there is potentially a lot of information here that currently we're not really taking advantage of in our community. For measuring, very briefly, measuring the Mueller matrix, you have a source and you have a detector, and you combine different polarizers on your source and detector in a variety of different ways to measure all of these different parameters. And like the S12, you cannot measure directly with a single measurement. You have to, so this is unpolarized for the source, unpolarized for the source, and then this is putting a vertical polarized analyzer in front of your detector. And this gives you S11 plus S21. And then if you rotate that analyzer, then you get S11 minus S21. So making those two measurements, you can then derive both S11 and S21. So that's how you do it. So that really the only measurement of the Mueller matrix that's ever been done that I know of for whole water in the ocean was by Voss and Fry in 1984. And this was averaged from the Atlantic and Pacific Oceans for over 60 samples. And as you can see, this is S13 and S14 are flat, so it's randomly oriented particles, which is what you'd expect because they're collecting a sample, bringing it to the ship, putting it in a cuvette, and making the measurement. There's a lot of other zero elements as well. This is the S12 normalized to S11. So this is also called the degree of linear polarization. And this, for comparison, is the Mueller matrix calculated for very, very small particles relative to the wavelength of light called Rayleigh scatters. And these particles will completely depolarize the beam at 90 degrees, at exactly 90 degrees. So this is 0 to 180 for all the plots here, and -1 to 0. So it goes to -1. So it's completely depolarized. So you see some depolarization in typical ocean water, but it's not all the way to 1, which is very interesting. I'll show some more data on that in a second. You can see that the S12 and the S21 are essentially mirror images. This is the circular polarization, and then for Rayleigh, you can see the circular polarization goes all the way to -1 here. You don't quite get there, just like with the depolarization of the linear light with the vertical. And then this is S22, which is an index of non-sphericity. And if this is homogeneous spherical particles, this will be 1 all the way across at all angles. And you can see that they have a deviation here that goes down about 0.8, indicating that there's a lot of non-spherical particles, which is what you'd expect. The whole ocean is filled with non-spherical particles. Yeah?
These measurements are assuming azimuthal independence?
Yes.
Okay.
Yeah.
So that will maybe add some constraint to the matrix.
Azimuthal symmetry.
Azimuthal symmetry. Yeah. Okay.
So this is some measurements that we've made with the Mascot VSF device. This is a vertical profile of just beta theta. So you've got 10 degrees here to 170 degrees. You can see some structure. And then this is S12, second parameter. So the degree of linear polarization is a function of angle. And this curve here is the Rayleigh, so you have complete depolarization at 90 degrees. And our measurements here, integrated through the whole water column, average through the whole water column, is this blue curve here. So we have about 0.8 average through the entire water column. And I've overlaid here Voss and Fry measurements in cyan, and then 2 other measurements by Katiszewicz in 1976 and 1977. But what's really interesting is very, very few people have looked at the degree of linear polarization. And we're starting to talk about putting polarimeters in space to look at polarized scattering in the ocean, and using LiDAR systems to look at the return of polarized radiation in the ocean. And we know very, very little about polarized scattering. So it's really an area where a lot of work needs to be done. This here is plotting this shape throughout the entire water column. So you can see that there's a very strong degree of linear polarization at the surface. So this 1 here corresponds to this curve, which is about 0.9. And then once you get to this deep layer, which is dominated by suspended particles, mainly suspended sediments with higher refractive index, degree of linear polarization decreases substantially to about 0.6. So in a single vertical profile, it's ranging between about 0.6 and 0.9 in Santa Barbara Channel. I'll also mention too that it's the maximum is not exactly at 90 degrees. It's displaced a little to larger angles. And we have to kind of infer that because we only have 10-degree increments with the mascot data. But Voss and Fry also saw that as well. So yeah, there's a lot of information here about the refractive index, composition of the particles, the size distribution, particle shape, particle orientation. We've done some modeling with me theory to try to interpret some of these degree of linear polarization measurements that we've made, but we're still trying to figure out just what it all means. Much to be done. So now I'm going to transition to looking at the scattering components. And this is the same breakdown that Zhongping used in his talk, where we have pure seawater, turbulence, or refractive index discontinuities, particles, and bubbles. And it's kind of a philosophical argument whether or not you want to call a bubble a particle. But it's good to separate them, I think, because bubbles are just such a unique and different scattering agent in the ocean. So with seawater scattering, the first real comprehensive work was by Morel in 1974. It's really an excellent paper where he goes through all the physics of the Einstein-Smoluchowski theory. And he makes all the computations. And what we did was we modeled scattering as a function of wavelength based on those computations and put them in this equation. This here is representing the effect of salts. It's all based on a single measurement from Morel's experimental data from 1968, where he took Mediterranean water, probably from right outside in the harbor here. It's 37 parts per thousand, and he found that there was 30% scattering, 30% increase in scattering at 37 parts per thousand. We assume the relationship is linear, and that's how salts are added to pure water scattering when we make calculations. This is a big unknown. I mean, Morel is probably the best, in my opinion, probably the best experimentalist in ocean optics. And his experimental data from the 60s even are remarkable, stuff that people haven't really been able to reproduce. So I'm sure this value is very, very good, but still, it needs to be reproduced contemporarily, and we need to know that. Because if just a few percent off, as I'll talk about later, it has a dramatic effect, especially in clear water, when we try to then subtract water to get the particulate fraction. All right? So, and then this term here is looking at the depolarization of pure water scattering. It's molecular scattering, but like Rayleigh scattering, but it doesn't perfectly depolarize at 90 degrees. So that's what this coefficient controls, the depolarization ratio. And this is another area where we really don't have a good number for this. So this is currently not the best method, but I just wanted to point it out because everything pre-2006 pretty much uses this method. Then in 2007, 2008, we were using Buteveld's recommendation of using the same equations as Morel did, updating the coefficients. And now the exponent that Morel came up with, is 4.32, is now 4.14. And what's very important is that they changed the depolarization ratio from 0.09 to 0.051. This is kind of really getting in the details, but it's kind of important, so I'm going to go over it. And this all came from one paper by Farinado and Rawell in 1974. And they actually made this measurement in multiple ways through different experimental setups, different geometries for the setup, and they got different numbers. So Buteveld thought this was the best number, and that's what he put here, but it's currently not the best method. So this is the best method. And this is what we've been using since about 2009. This is Xiaodong Zhang, something that he came up with. He uses the same theory, but there's two ways to express the theory. You can express it in terms of a density derivative or a pressure derivative. Not a big deal, but he chose the density derivative. Actually doesn't make too much of a difference. But he used a lower depolarization ratio because in the same paper, they came up with this one as well. It's actually a dramatically different number. You go from 0.09 with Morel, 0.051, 0.039. And it's a critical area of uncertainty that needs further work. So these values are most accurate. They're probably 2 to 4% within, true pure water scattering, but this is a critical area of uncertainty that we just don't know. And then, of course, if you want to, since it's symmetric around 90 degrees, if you want backscattering, you divide by 2. So this kind of summarizes some of those values. So this is all relative to Buteveld's values at 0. So here are Morell's values. And there's also a paper by Smith and Baker that was used extensively for many, many years. This is a Smith and Baker 1981, where they had, the title was like the optical properties of pure seawater, something like that. For the scattering part, they essentially took Morell's data and just transcribed it to the paper. But there was a truncation problem, so it's a lot more, it shows a lot more scatter than Morell's actual data. And then this is Morell's actual data here, which I'm fitting. This is a recommendation by Schifrin, Kusil Schifrin, a great ocean optics guru from Russia, who came over to the States after everything happened. And then this is Morell's experimental data here. So Morell's experimental data is much lower than these. I didn't plot Xiaodong Zhang's data, but Xiaodong Zhang's data now is like right down in here. So it's just maybe a couple % higher than Morell's experimental data. The main difference between all of these, they use different coefficients for something, but the main difference is that depolarization ratio. So you can see what a huge effect it has. It's going from 0.09 to 0.051 to 0.039. And again, the 0.051 and the 0.039 were in the same paper, and they just used different setups and they got different numbers. So it's a really important area of uncertainty. And because backscattering by pure seawater can be 80–90% of your total backscattering signal, and if you're interested in the particulate fraction, BBP, you have to subtract that. So if you've got, say, plus or minus 5% uncertainty, and pure seawater backscattering is, say, 85% of your total signal, well, if you use one or the other, you're going to double your particle contribution to backscattering. So it's really important to nail this down. So I'll jump to turbulence, which Zhangping mentioned. This is really refractive index discontinuities in the water. So this is density fluctuations due to temperature and salinity differences on very small scales. Because you can have turbulence, you can move the water around in the small scale physics, but if you don't have the reflective index discontinuities, you're not going to see that light being scattered in the near forward. But this is showing, so this is again log. This goes from a very small number to 0.057 degrees, so we're looking at just the near forward. And this paper by Derek Bogutsky et al. Quantified the scattering due to that particular turbulence. Turbulence can affect, depending on the relative magnitude of these refractive index discontinuities, it can scatter out to about 0.1. In some cases, if the refractive index discontinuities are very large, you can go even higher. But it's typically not included in attenuation measurements because you've got this acceptance angle issue. The acceptance angle is usually large enough so that you're not including effects of turbulence. The exception is the LIST. The LIST can see turbulence. We have an example of that. So this is that same near-forward diffractometer that I was talking to you guys about before, where this light goes through a sample of water, it's scattered, and all the light scattered in a specific direction hits a lens that focuses it down onto a detector. And so the small angle scattering detectors are here, and the large angle scattering detectors are here. And if you look at the volume scattering function, this is a plot I showed before in the beginning. For particles, you'd expect this volume scattering function to just kind of careen off, and then when you go to 0, it's almost flat. So this stuff here is really due to density fluctuations at the small angles. And you can see that with the list. So if you calculate refractive index discontinuities from temperature and salinity, this is what you get. So there's obviously a strong density stair step right here. And then you know how I was telling you about this inversion that you do with the list to get particle sizes, where there's 32 different particle VSFs that are then used in this library in the inversion. What we did was, you look at, this has a specific shape for turbulence. So we added that to the library. So it was something that we could invert for, and then we could plot it. And this is what that looked like. So you see a very strong effect to that scattering, that turbulence effect in this density discontinuity. And you also see, smaller effects in other areas as well. Moving on to particles, this is the Petzold volume scattering function. Again, he's got two that I'm plotting here. He's got others that he measured. But this is San Diego Harbor in green, and the blue is AUTEC, which is tongue of the ocean, Bahamas. And then this is pure water here. And again, there were exceedingly few measurements of the VSF until recent times. So literally for over 30 years, this was the go-to VSF of the community. And again, I want to reiterate that this can be a very, very significant fraction of your total backscattering. So it's important to consider its accuracy. Yeah.
You say that the turbulence makes effect by a change in the refractive index.
Mm-hmm.
How can you know if it's turbulence or not? Maybe the halocline or the thermocline. It would mean the same effect, or I don't know.
Yeah, it's really refractive index discontinuities.
That's what you're measuring. Okay.
Turbulence is just the mechanism by which it's moving those around and mixing them over time. Yeah. So I think Darius showed a very similar plot where you have a particle, in this case a sphere, you've got light hitting the particle, and then you have reflection, and you have refraction and reflection, and you can have multiple refractions and reflection. And then you've got transmission, and then you've got light that's also scattered around the particle that's diffracted. So it doesn't actually impinge on the cross-section of the particle, but it's still scattered. And I mentioned I was going to show this plot where these guys did the mean-theory calculation, which is the bold trace there of the volume scattering function for spheres, for a population of spheres. And they also calculated the contribution from diffraction and then transmission and reflection. So you can see that diffraction is really dominating, and this is a log scale, it's dominating in the first, say, 10 degrees. So Darius mentioned this, I'm just going to go over it real quick. But for a collection of particles that are identical, they have a certain scattering efficiency, and again, that's the fraction of light that's hitting the cross-section that is going to be attenuated or scattered. So you could, I say CP or BP or BBP because this C here, you could just substitute B or BB. So if this is 1, that means all the light hitting that particle is scattered, and if it's 0, none of it is. This is the cross-sectional area of the particle, so we're assuming for the time being that it's a sphere, something close to a sphere, and the number per volume, which is it's really a very simple relationship. And then you can approximate the size distribution of particles a variety of ways. One way that's often done that is really quite a good approximation, although many in the field will argue with that. It's not perfect, but for the purposes of modeling optics, there's a lot of really great reasons why this is an very good approximation for most particle size distributions. And it's just a power law. Very simple. And then you can combine them, and you get this for a population of spheres. And widely varying natural size distributions, so that slope of this, so that this S here, slope of that power law regression for the, that power law fit for the size distributions, and widely varying refractive indexes for different composition particles is the reason why connecting things like optical properties to biogeochemical properties we care about is challenging sometimes. Those relationships vary. And so, yeah, I think Darius probably mentioned these along with other reviews by Morel and Bricot. But these two in particular have always been dear to my heart. I've read them a lot. I still read them. They're really fantastic reviews. And really anything by Morel you should download and read, if you want to be in ocean optics. All of his work is really outstanding. Villefranche actually has a great website for all the publications that ever came out of Villefranche. And you could spend a whole day just downloading some great publications there. I highly recommend it. So we got this from the previous page, combining size distribution with the derivation of C. And then Q follows this kind of pattern. Darius showed a few of these. And there's also an approximation that Van der Hulst came up with, where instead of going through a whole me theory, he's got a very simple approximation that will give you basically that same shape. And that's actually the approximation that Fournier and Ferrand further approximated in their algorithm for the phase function analytical model. But what's interesting is that for the small particles here, and small particles, and I should mention the Van der Hulst approximation only works for particles with relatively low refractive index relative to the median. So certainly for cells it works well because they're soft and they have a cytoplasm that has a similar refractive index to the surrounding medium. So for small particles here, this is a relatively linear relationship. So you plug that into here. For the small particles, CP is proportional to particle volume. And then as this reaches this asymptote of 2, so again, you're actually attenuating or scattering twice as much energy that's impinging on the particle because of diffraction. Then you start to get attenuation coefficient or scattering coefficient that is proportional to the total surface area of the particle population or the cross-sectional area. And this, in most cases, this is a pretty good approximation that your CP is proportional to the total cross-sectional area of your population. So there's a great quote from a paper that Darius and Emmanuel and others published in 2004, saying, "Our present-day interpretation and detailed understanding of major sources of backscattering and its variability in the ocean are uncertain and controversial." Which is very true. It's very true today. And for us in the field, it's actually great because it means there's a lot of work to do. And one thing Darius pointed out very early on is that if you look at the scattering from phytoplankton, relatively soft particles, there seems to be an enigma in that you don't have enough scattering to account for the levels that you see in remote sensing reflectance. So this is all based on modeling, which is just about the best we could do. So the question is, why is that the case? And either there's other particles, like detrital particles, that are covarying with the phytoplankton, and they're the ones responsible for the backscattering, but they have to covary very, very closely because remote sensing reflectance works pretty well when we invert it to get chlorophyll and other parameters that are directly related to phytoplankton. Or the phytoplankton are, just by virtue of being very complex, perhaps they have more backscattering than we're accounting for. So quickly, we had a project to look at this kind of complex particle hypothesis. Are they scattering more light than we'd expect based on their relatively low refractive index? And we cooked up 3 cultures, 2 diatoms and a dinoflagellate, different sizes, and measured the scattering properties in the cultures. What's really important is there's a lot of published backscattering measurements that were made in cultures. And you have to be very, very careful about the background because you have a lot of stuff in a culture besides just the organisms that are growing there. And I know that a lot of the work that's been done, they're very, very careful with dilution. You can do things like gently spin them down and then resuspend in very, very fresh filtered media. So you can do things like that. But you have to be very careful. And so what we did was we measured the total scattering parameters. Then we filtered out very gently the phytoplankton particles with a 10 micron NITEX screen to look at the background contribution. And this was the background contribution. And this is the backscattering ratio of that. But it's very, very high. It's very significant. So it's something that at least needs to be considered. And there are instances where it hasn't been. So this is the backscattering ratio for these different cultures. So the relative amount of backscattering we're looking at here. And this is what we measured. And then this was a different way of modeling it here. But using me theory, we obtained backscattering ratios that were very low, half or lower than what we actually measured. But then we put a coat on the particles, which is very consistent with what these phytoplankton actually look like. So they have a shell a frustule, a glass frustule that has a higher refractive index. So we used a refractive index of 1.1 for that. And then we got values that were fairly comparable with what we measured. In this case, it wasn't for this colony-forming diatom, but there was another method that we used that I'm not going to go into, but where it looked pretty close. Then we wanted to see, so this is evidence that the shell is important in backscattering, and then we wanted to see if we could visualize in a particle where the backscattering was coming from. So with a standard microscope with your sample on a glass slide here, we mounted a laser on the side, and then we turned off the lamp of the microscope so we could try to image backscattering from the particles. So we did this with a bunch of different ones, but I'm showing you one here from a Thalassiocyra diatom, where each of these cells kind of looks like a pillbox, like a Petri dish. And this is what the, you can't see it very well in the light, but this is what the backscattering image looked like. And this is a close-up of one of the cells. And you can see there's some very faint contribution from within the cell, the cytoplasm and the organelles, et cetera. But the outside shell is really, really critical. And so this is what the cell looks like. You kind of have a Petri dish. And you can actually take a Petri dish and just shine a laser through the side, and the sides will glow exactly like that. So it's a good indication that the shell is important in backscattering. Another clue is that we've looked at this backscattering ratio in a lot of different places. So the Gulf of California in 2001, and through another paper we looked at it in 9 different locations around the United States. And you get really very similar relationships. And very interestingly, there's always this kind of 0.5% floor where you don't see backscattering ratios below that amount, or it's very rare. Even at very, very high chlorophyll concentrations, where presumably particle population is going to be very, very strongly influenced by the phytoplankton, you never see it fall below that level. So this is some phytoplankton backscattering ratio work that Valancourt et al. Did for 28 different populations here. And then this is that 0.5% floor that I showed from the field work. You can see in many cases it's below, but it kind of oscillates around it. This is one case too where they didn't mention what they did with the background in the cultures, and I'm not sure how clean that was, but anyway, it's sort of consistent. And then if you calculate the scattering properties, this backscattering ratio, if you assume all these particles are homogeneous spheres, you get this range with a median here. So it's much, much lower than what was observed and where we're getting in our values in the field. And then if you use a coded sphere model, though, you start to get into this area here where the field results and our very limited culture measurements and this coded sphere modeling start to agree. So I would infer from this that phytoplankton do likely make a significant direct contribution to backscattering. And it's something that, you know, is part of one of those controversial, interesting issues in our field. It's an area of work that I would encourage you guys to pursue. This is another clue as well. This is in Monterey Bay, this is a layer of a kishiwo. It's a dinoflagellate that's mobile. And every day, this would migrate through the whole water column. So during the night, it would come down to deeper levels and get nutrients, and then during the day, it would come to the surface and get light. And we looked at the optical properties, and you can see there's a background here. There's a bunch of things that are plotted. But the green here is the chlorophyll, and the backscattering ratio, particular backscattering ratio, is the blue here. So you can see there's a decrease in the backscattering ratio where you have the high chlorophyll concentration. But as this moved through the water column, you kind of see that decrease, this minimum here, kind of go up and down through the water column, superimposed on everything else that's in there. And because they're migrating, you can kind of say, okay, we've got a background here, and then they're migrating below, and so they're adding essentially to the optical properties that are there. So from that, we deduced that there's about 20% of the signal was coming from the kishiwo. So here's at least some evidence, if our assumptions about them not affecting those optical properties in that background as they move through it, if that's true, then they're contributing some. There was a lot of background here as well, but they're making some contribution. And just to point out, too, that others with benchtop instruments like Witkowski et al. 1998 have measured the volume scattering function, not only volume scattering function, but the whole Mueller matrix elements for phytoplankton, in this case, chlorella. And these are measurements that were made by Volton. So he measured F11 and the depolarization, a degree of linear polarization, so F12 over F11 for 15 different phytoplankton species and 2 different sediment samples. What's kind of interesting in all of these measurements, these are vastly different types of phytoplankton, and then here we have sediment, and all of the VSFs generally look monotonic, quite similar in shape, and quite similar in shape to what we see in the ocean. So there's also been a lot of effort over the years in trying to model the scattering properties of phytoplankton. So everything I've shown you before, pretty much has been measurements. People have used Rayleigh scattering. So this is scattering for very, very small particles. It's really a very simple relationship that you can use to approximate their scattering. Lorentz mean theory, which we've talked some about, and there's coded sphere versions like the one I just mentioned for the experiment. There's multi-layer sphere versions. It's been used very extensively, and it's very convenient too. It's something that encompasses Rayleigh all the way to very, very large particles, and it runs quickly. So it's something that's convenient to use. I mentioned the Van der Waals approximation, which is a good fit to Mie theory for a specific size range of particles, and when you have low n relative to the medium. Geometric optics, so it's just ray tracing. And there have been efforts recently, there's something called IGOM, Improved Geometric Optics Method that was developed in George Kadawar's lab. This is ray by ray. So this is good for larger particles, and it runs relatively fast. You can't use it for smaller particles. Discrete dipole approximation, I think Darius mentioned this, where you take a cell or whatever particle you're interested in and subdivide into all these small dipoles and then look at the scattering from each one individually and then bring it all together. Finite difference time domain, pseudospectral time domain, and then T-matrix, which is a very popular method to use for small particles, but you can't use it for big particles because it's computationally very, very intensive. There's been a bunch of different versions that have been developed over the years, many in George Kadawar's lab, like the invariant betting, et cetera, et cetera. But it's important to realize that all of these have restrictions in terms of the size ranges they can be used, the refractive index range they can be used, the shape, and sometimes the symmetries of the particles themselves. And what's often done is that you're going to take one model that's using a certain size range for a certain refractive index and another for another size range, and then you're trying to kind of combine them all to get an overall volume scattering function for your population. So this, from what I can tell, this is out of George Kadawar's lab. Bing Qiang's son is a postdoc who's worked with us, and he made calculations with a bunch of different models for, from a modeling point of view, a very complex particle. So this was trying to approximate scattering from a didelin particle, so a chain-forming triangular prism diatom, and we stuck a nucleus in there as well, a spherical nucleus. And the dimensions were all consistent with the actual dimensions that we've looked under the microscope and got those formed. And so here they're combining 2 different methods. This is a T-matrix and a geometric optics for large particles. And they've calculated the S11 here, the phase function, and then some of the polarization characteristics of these particles. This looks pretty reasonable here, and you don't see a lot of wiggles, which is, I think, the more complex the particle gets, typically the oscillations that you'd see with typical Mie theory start to go away. But certain things, like you see, this almost looks like pure Rayleigh scattering, which doesn't really make much sense to me. I can't really figure that out. You see complete depolarization at 90 degrees, and these are 10 nanometer or 10 micron length particles. And then the circular polarization also looks just like Rayleigh theory. So there's still aspects that we're trying to work out. They've also made calculations for us for asymmetric hexahedra. So you're taking a hexahedra and then you take one of the sides and you kink it a little bit. So that way you don't get this resonance scattering between parallel layers. And so this is a very good approximation we're finding for mineral particles, like quartz, sand. And these are the different volume scattering, or the phase functions that were calculated for an entire polydispersion here. Well, each one is representative of a single size. And then again, this is a combination of two different models, one for the small particles and the IGOM for the large particles. And then to move on to bubbles, bubbles have unique scattering in the respect that they have this mid-angle enhancement that peaks at about 70, 80 degrees. The enhancement peaks at 70, 80 degrees. And it's very easy to see this in measurements with the volume scattering function device that we have. So these are actual measurements that came from Scripps-Pierce surf zone. And when you have sediment plumes go by, the red curve, the red VSF is what you get. When you have bubble plumes go by, you get this mid-angle enhancement here. And then the blue is sort of the background. But optics, it's interesting because optics is one of the only methods to really resolve concentration of small bubbles when you start to get into just a few microns. There are other techniques to resolve bubbles like acoustics, but they're looking at very large bubbles, like at least tens of microns. They can get down to about 20. What's also interesting about bubbles, I should mention too that the reason you get this mid-angle enhancement is because there's a very strong refractive index difference between bubbles, which is 1, and the outside medium, which is 1.34. So the relative refractive index is 0.75. What you get is total internal reflection in the medium. So you have total internal reflection essentially out to here, and then you start getting through the particle at angles larger than that. And that's when you look at polarized scattering from these guys. So this is looking at the degree of linear polarization again, then S12 over S11. This is the background here. Bubbles look totally different. You basically don't see any depolarization out to that total internal reflection angle, and then it jumps up. So it has a really unique curve. And when you're making measurements in the field, we can see the background, and then we can see bubbles that agree with me theory very, very well. And then depending on the relative concentration of bubbles, we see curves in between. But this is all because of that total internal reflection. And then I think, yeah. So the final aspect of particle scattering I wanted to mention was anomalous dispersion, which is a spectral property. I really haven't talked about spectral properties much at all. And to be honest, when we talk about spectral properties with backscattering, we haven't had the instrumentation to really resolve that experimentally. So most of what we use in models and algorithms, et cetera, those are kind of idealized modeling based spectra of backscattering. And what happens when you have absorption peaks is that absorption can affect the refractive index of your particles, and the refractive index affects your Q, so it affects your scattering efficiency, it reduces your scattering efficiency. This is work by Darius et al. From 1988. So this is the imaginary refractive index, which is closely linked to absorption, particulate absorption. And then this is the variation that you see in the refractive index due to this absorption from an anomalous dispersion. And then this is looking at the effect for a single particle absorption peak. So you actually see a decrease in refractive index, then there's a strong gradient through the peak, and then you see a peak in the enhancement of refractive index on the long wavelength side of the particle. So it's something you just need to be aware of. When you change the absorption, you can change the scattering. So how are we doing on time? So, all right. I guess I'll start this, but I don't think I'll get through it. So the break's at 10:30? Yeah, okay. So now I'm going to talk about the actual measurements. I've shown this plot a few times, and it's just a good illustration of some of the challenges in making measurements of the VSF. So you've got several orders of magnitude here that you need to resolve if you want to resolve the entire VSF. As I mentioned, you need to typically use a different instrument for the near forward relative to the larger angles, and if you're going to measure beta 180, you need a different instrument for that as well. So if you're really going to resolve the entire VSF, you would really need 3 different sensors to do that. But even in the angles that we're resolving here, the 10 to 170 range with the mascot, you still have several orders of magnitude variation in intensity that you need to resolve in a single VSF. And then in just the natural environment, you see a very large dynamic range. So the overall range that you need to resolve, if you had a single detector, like is shown here, where this source is going to rotate around, you're going to measure it with a single receiver, you're talking like 10 to the 10, something like that at least. So it makes it a challenge. There's also rapid temporal variability, especially in surface waters where you have breaking waves. We made a lot of measurements in surf zones for various reasons. Rejecting ambient light is also important. When you're at the surface, there's a lot of ambient light, and especially here, you're trying to detect a signal that's very, very low. So it's easily on the order, or if not lower, than the ambient light. So you need to account for that. And then when you go to calibrate this sensor, there isn't an absolute standard. You can't go out and buy from Sigma or somebody a vat of a solution that has an exact volume scattering function. So you have to kind of get around that. I'll talk about that in a minute. There's a variety of sensors to measure scattering now, and a few are on the market. And this is one of them. This is the Wet Labs Eco sensors, and there's a bunch of different flavors of these. You can see they're quite small. This guy's holding it. It's maybe like the size of a hockey puck. And some have shutters. There's different wavelengths you can get. There's different angles you can get in the backward direction. This is a BB9, so this is measuring 9 different wavelengths of backscattering, or really the volume scattering function people then use to get backscattering, derive backscattering, which I'll talk about later. And then these sensors are conveniently installed on a bunch of different autonomous vehicles as well. And if you have a shutter on it, you can put it on a mooring, and it can maintain very good measurements without biofouling or really much drift for many months. And then this is a figure showing at each one of these source detector pairs kind of what the geometry looks like. You have a source beam that comes out, and then you have a detector beam, and where they intersect is your sample volume right in front of the sensor face. So I've been talking a lot about the mascot sensor that it's a prototype that we have. We actually have 2 of them. And it's an array of detectors instead of a single detector that rotates like this, or a single source that rotates. And the reason we did that is because then you can tune each detector for its specific dynamic range that it needs to resolve. So these are tuned the gain on these is much lower than the gain on these. There's a red source at 658 nanometers, and then each one of the detectors is imaged to, it's not exact, it should be like right in the middle there. So they're all imaged to the same sample volume right here. Now, they all have subtly different sample volumes because of the geometry of the intersection. But as this says, the detector field of views vary. So they're very narrow here, and as we go to larger angles, the field of views opened up. And we can do that because there's a lot of light here, so we have really good signal. We can have a narrow field of view, and then since the VSF is very, very steep here, we don't want to smear it by having an open field of view. It has a 20 hertz sampling rate, so we can resolve some of the dynamics of bubble plumes, that kind of thing, and surface waters. And this is the lasers in here, the laser sources in here, and it goes through a wedge depolarizer so that we have unpolarized light emerging into the water. This is the mascot deployed on one of our sensor packages, and then this is also the list device. So I showed a lot of data that's combined the list and the mascot, and this is how we deploy it in the field. So this is another device, the MVSM, developed by these guys in Ukraine. And here's a picture of it. This is the version that's at the Naval Research Lab right now with Derek Gray and Alan Weideman. They call it the Beast. And then here's the geometry of the optics. So you have a source, and you have a detector. And then you also have a detector over here for measuring transmission. And they have this really interesting periscope prism. And this is the only thing that moves in the whole design. So this thing rotates around. As it rotates around, whatever it's getting through here is reflected and imaged onto this detector. And then something that can go in the water. It was in a profiling cage, but they use it mostly, well, they use it both in the surface water as well as taking samples and putting it in on deck. This is a device, the Pole VSM, that was developed here at the Laboratoire Oceanographic, Villefranche. Is it here right now? Do you know?
I'm not sure.
It'd be interesting to take a tour and.
The instrument might still be here.
Yeah. So this is an interesting design. It's a benchtop design, obviously, but there's a vat full of your fluid here, and then there's two prism towers that go in the water. And one has the laser source emerging through it, and then the other one is for the detector. And the logic behind this is that whenever you have cuvettes in the lab and you're sending light through the cuvettes, you get scattering, and the scattering can contaminate your VSF. Particularly, it's really insidious in these kind of arrangements in the backward direction. So a lot of VSFs for benchtop VSF devices, you see it come down nice and smooth, and it flattens out, and then at the very end here you see an uptick, typically because of scattering within the cuvette. So this is designed to kind of remove that. And then this is the, this is a mirror here which removes the beam, and then this is the detector. So the detector is imaged to the very middle of this beam going through the water. It rotates around, and you can resolve the volume scattering function. So I mentioned the list a lot. This is a diffractometer measuring near-forward scattering. It uses a different technique, diffractometry, where all the light scattered in a specific direction is focused with the lens onto its own specific detector. We actually took the list apart. I don't think you could find this anywhere. We took the list apart, and Matt sketched out the exact location of all the different detectors. So you can see they're all shaped in annular rings. All right, remember that unit sphere and the projecting on the annular ring for the solid angle? And they're looking at just a fraction of it. So most of these, I think, are 16ths. Then you get down to fourths and smaller increments there. But that's how all the 32 measurements are made. And then there's also a transmission measurement that's made. There's a hole right in the middle here, and you have a transmission detector with collimating optics in front of it. And this is what it looks like, the actual instrument. So the laser is actually over here, and it's pumped with an optical fiber down to here, and the beam goes this way. And the reason it's so long is because you've got all of this optics here that you need to put in here. When you want to measure near-forward light, the more towards the near-forward you get, the longer focal length you need on that lens. And then they've also recently come out with a list VSF. I should mention that the Ecos are commercially available. The List 100X is commercially available, and now this is commercially available. So to my knowledge, I think this is the only commercially available volume scattering function device on the market.
Is Mascot going to become commercially available?
We really campaigned for that at Wet Labs for a long time, and there's a lot of people in the community that did as well, and the powers that be never pursued it. That's all I can say. I think it could be commercialized now, and we're at a point now where those sensors they're over 10 years, they're about 10 years old, and they're starting to have problems, and we really need to get the next generation sensor built. I'm hoping to do that at Harbor Branch, and then maybe once that's done, it might be a good time to pursue commercialization of that. So what this does, this is an eyeball, and this is a really difficult image to kind of see what's going on. I found it on the web last night, but you've got this laser here. It can be either a green laser or a red laser, and then you've got this prism here in the eyeball. And so it's rotating like this. So this is the light that's scattered from the beam. It goes through this face, bounces off this part of the reflective prism, and then goes to the detector over here. And so as it rotates around, it's essentially imaging scattering on different parts of that laser beam throughout this entire sample volume here. And then optics in here are the exact same as the LIST 100X. So it's measuring the near forward as well. So combining the two, you get the full VSF in one device, which is really nice. So I've never used one of these. Wayne Slade, I've seen use them a lot on cruises in the recent year or two, and anxious to see some results from it. I'll also mention an IVSF that was developed at that institution in Germany, and I was recently on a cruise last year where this was deployed. It's very interesting. So there's a scattering volume here. There's a primary beam that goes through it, and then all the reflected light from representing the VSF hits this kind of reflecting prism, this kind of circular reflective prism, goes through the slit and is eventually imaged onto a CCD camera. And then through calibrations, et cetera, you can get the VSF. So I felt compelled to measure to mention turbidity, or NTUs. You guys have probably heard of these sensors. From an optics, a rigorous optics standpoint, they're typically not sensors you want to use, unless you have a turbidity sensor that you calibrated in a rigorous way, so it was giving you rigorous information about scattering. They're typically a measurement of scattering at 90 degrees, but every turbidity sensor really measures at a different centroid angle and with a different weighting function around that centroid angle. And because even at 90 degrees, the VSF is starting to slope up pretty steeply. If you've got plus or minus 5 degrees or plus or minus 10 degrees, you're going to get a totally different answer. The eco turbidity sensors, eco FLNTUs that wet lab sells, actually measure turbidity at 140 degrees. So all companies seem to pick different angles. There are some rigorous, quote unquote, rigorous specifications for this from the EPA. Like it should be at 90 degrees. It should be, I think, white light. I forget exactly what they're, because different agencies have different definitions. But it's not precise enough. It doesn't say, for instance, what the weighting function around the 90-degree scattering should be, which is really important. And they're calibrated typically to formosym particles, which are kind of Rayleigh-like, very, very small. And the phase function looks nothing like that of the real ocean. So even though a nephelometric turbidity unit sounds like a rigorous engineering unit, it's not. And virtually every turbidity measurement in NTU will give you a different answer. And it's also not the best metric for water clarity either. C is the best metric for this, which is directly linked to visibility. Yeah, the signal may be correlated with backscattering. You can certainly take any kind of turbidity sensor as long as it's measuring something consistent and calibrate it in a rigorous way if you know its geometry to get a rigorous scattering coefficient out of it. So now I'm going to go into the calibration, and this might be the perfect time to take a break. I'm going to talk about calibration of the sensors, but I'm not going to go into the weeds very much, because we really could get in the weeds. I'm sure there's probably one or two of you who might be interested, and I'd be glad to have a beer and we talk about it.
The results.
No, please go.
Okay. The results you showed about the cultures with me and the coating. Is this published?
No.
Okay.
It's presented at a meeting, but.
Continue.
But is your presentation online?
No.
Okay.
I could get it to you.
Okay.
I have a question. I'm no longer sure about this design 2009 reformulation for pure water backscattering. What are they doing for salinity effects?
They're calculating it independently,
Okay, so that's.
but it's all modeled.
Yeah, that's no longer the 35% increase. That's something.
Correct.
Yeah. Okay.
Correct.
So that's what you recommend.
Yes, that's what, and Jiaodong has this code where you plug in temperature, salinity, and angle range you want to calculate it, and it does everything for you. But it's still modeled. So I as you can tell, I'm kind of an experimentalist at heart, so I'd love to see the Morel work. reproduced again. And if it's a 30% effect, it's actually a very large effect. Even eco-sensors are resolving pure water scattering, pure seawater scattering. So it's typically like 7 to 10 digital counts out of a 4,000 count range, but the signal to noise is typically like 1 count. So you can resolve pure water scattering, and if it's 30%, even with an eco-sensor, Mascot's a lot more sensitive, and certainly with a benchtop device, you could make much higher resolution measurements, much higher fidelity measurements, especially since you're filtering out all the particles. With the benchtop measurement, the real challenge is all the particles, because all the particles are scattering light everywhere. There's internal reflections that you just, almost impossible to get rid of, and you have to usually model it out. But if you have just molecular scattering, you're still going to have some scattering, but it's not going to be at the level that you have with
yeah, because I think the most difficult part actually would be to produce so-called pure water, pure seawater, pure water. That's maybe the most difficult part of the exercise.
Right, right.
Because measuring the VSF or whatever might be, but then if your pure water is not pure because still you have some particles or whatever. And I guess that's maybe the most difficult and painful part of the process.
Yeah. Or if you have water that's not pure, but you just add pure salts, if you can do that, but then you have the problem of purifying the salts. And you're looking at just the effects of the salts. But you're absolutely right, and I'm sure Darius and you guys have talked to Andre about this when he was around, but he used to talk about just how difficult it was in that experiment to get that absolutely pure water. And it was pure for about 5 minutes, and then, because it just started, once you get it that pure, it's such an incredible solvent, it starts to scavenge, even like a glass container will start to eat away the glass. It's incredibly active solution.